Welcome to Mary Beth Price book, Chapter 8, Raster Analysis. This is from Mastering ArcGIS, the 5th edition. Notice this is copyright 2011, so this is the 5th edition. For GIS 311, these are the skills you must know in Lab 8. You'll download some national elevation datasets. You'll project a raster. We'll do some resampling, extract by mask, which is similar to a clip from previous labs. Create a hillshade, rendering. We've used one, but we haven't created one. Create a slope rendering, adjust transparency. You've done that. Reclassify and raster to vector transformation. You will be using some old skills: extract data, project shapefiles, clear the on-the-fly projection. You'll do a buffer, vector symbology of many sorts, select by attribute, select by location, and a bunch of other basic steps while you complete Lab 8. This chapter goes beyond where we need to do in rasters. Therefore, for 311, it will be cut short. This is a raster data model. It is on the right. We have a georeference to the Earth's surface with an XY location is always on the top left, and of course we have columns and rows. This is a cellular model. It is in basic little cells similar to a JPEG. Here we have some more pixels, and in this case we're told that the resolution is 30 meters by 30 meters. Each pixel contains just one numeric value. The dimensions of the pixel vary by the grid that you're using. In this case, the resolution is 30 by 30. The value represents some property of that pixel area, such as elevation or rainfall. Perhaps this could be rainfall. This area gets 1 inch. This area gets 4, which is highly unlikely. It's more so that these are more codes for land use, perhaps. Values may be integers or floating point numbers. And again, unlike a polygon, each cell only has one attribute, and that's its value. If you need to store multiple values, that means you're storing multiple rasters. I'm going to skip through this very quickly because ArcGIS does most of it for us, and there is no need at this time to belabor these points. But we're using binary data. Most raster formats use that method. Is stored as a series of zeros and ones representing numbers in base 2. And binary values are grouped by 8. Pixel depth. The number of bytes used for each pixel. More bytes equals larger numbers, which means more space. And here we have an 8-bit, 16-bit, and 24-bit pixel storing 1 byte, 2 bytes, or 3 bytes. Again, going to zip through it very quickly. Types of raster values. We can have discrete rasters, such as land values. This is code 10, code 14, code 13, code 10 again. Here's a discrete raster with roads. Notice how it's jumpy because it's not a very good resolution. Here we have a continuous raster or digital elevation model, and then another continuous raster which is an image, and these values are the color values, or in this case gray values. Raster properties. When you're looking into layer properties, be sure to scroll down for more information. Here's another raster. Bands. A single raster may include multiple arrays, more often used to store color images and satellite images. Here is a 7-band Landsat satellite image. Notice the different color bands. Why do we use rasters? They're better at storing certain kinds of data and also analyzing certain types of data. It's often faster because we're dealing with a known value. We know the size of every pixel, and it's easy to calculate that value. If we know it's 30 by 30, throughout the raster, it's much easier to do some calculations. But the coordinate position or precision is generally lower. It has high precision because high precision has high storage costs, and you cannot store multiple attributes. Here are some examples of raster resolution. It's measured by cell dimension. Storage space increases as the square of the resolution. Here we have a vector format. Here we have a 200 meter raster of the same image. And here we have a 50 meter raster, which is 16 times bigger than this 200 meter raster. Cell size unit. Here's the linear unit, which is meter. The XY resolution units are based on the raster's coordinate system definition. Decimal degrees. Note the notation. Because distances and areas are fundamental to raster analysis, it is best to use projected coordinate systems for rasters. So we'll use a projection at all time. Usually it would be meters and feet. And of course that's or feet, not the same. In a raster analysis, we use cell-by-cell functions on one or more input grids. The cells must be the same size and line up spatially. Older software required the user to ensure that all input rasters had exactly the same size, shape, and aligned cell sizes. Resampling. If the input grids do not match, then one must be resampled to match the other. Resampling degrades the accuracy of a raster even if the difference in cell size and location is small. In this case, look at this grid of 4x4 cells. There's 1, 2, 3, 4. But if we're doing an analysis using a 3x3, we have to resample one of them. So if we resample this 4x4, it'll turn into this. And then it's obviously not as clear because we're using bigger areas and the resolution isn't as good. Here are some resampling methods. We will be using some of these. Nearest neighbor resampling. These are important to know. Grab the value from the old cell that falls at the center of the new cell. Preserves the original value and should always be used with categorical data, or as the original data values need to be preserved. It is also the fastest method. Bilinear calculates a new value from the 4 cells that fall the closest to the center of the new cell. It uses a distance-weighted algorithm based on the old cell centers, and it is best used with continuous data such as elevation. So up here we have categorical, and down here bilinear resampling we'll use it's used for continuous data, such as elevation or temperatures. Cubic convolution resampling calculates a new value from the 16 cells that fall closest to the center of the new cell. Distance-weighted algorithm based on the old cell centers. It is best used with continuous, such as elevation. It is the most time-consuming method, but as you can imagine, it may be the most accurate. The nice in the middle is the bilinear, although it cannot be used with categorical. ArcGIS automatically resamples rasters for analysis if needed without warning. Because resampling can degrade raster quality, users should be aware that this is happening. And these are some best practices. Strive to create and keep analysis data in aligned rasters with common extents and cell sizes. Use environment settings to enforce common grids for newly created rasters. And use the available resampling functions to prepare data so that you control how resampling happens rather than having the software do it automatically. We'll now move into some raster analysis techniques such as map algebra, Boolean overlay, and other functions. Raster analysis techniques. Here we have some simple map algebra. Rasters are essentially arrays of numbers. They can be added, subtracted, etc. Here we have an in-grid plus another in-grid, which gives us an out-grid. 7 plus 2 equals 9, 4 plus 6 equals 10, etc. That is called map algebra. Here's a conversion. We take our raster of precipitation in inches and convert it to a raster of precipitation in inches. Go from centimeters to inches. We divide by 2.54 and we get a new raster. Here's a cut and fill where we have initial surface minus the final surface. This is a model equation of map algebra. Complex expressions with multiple inputs to calculate a risk or hazard index. For example, runoff in centimeters based on 4 input grids: precipitation, slope, soil infiltration, and vegetation cover. Here is that formula. They first subtract vegetation from the erosion value, and then precipitation multiplied by 2 plus the slope, which was multiplied by 4. And then that raster would create a new raster, and you go with the new raster. Here's an elevation of greater than 1200 where 1 is true and 0 is false. We also take another raster where slope is less than 10, or for example we have crown cover less than 70 and the crown cover is greater than 40, and then we have a false or a true value that results. Boolean rasters represent maps of true and false states for a particular condition. Where is on this raster is the slope less than 10 degrees? Well, everywhere where it's a green would be yes, that is true. Elsewhere would be a 0, which is false. Boolean operators won't be using the XOR. We'll use some of these perhaps. This slide doesn't tell us very much, so we'll move on. Here's some more Boolean map algebra where 1 is true and 0 is false. So A and B. So you take A and B to get the right answer. And in this case, if it's a positive, then it's going to be the same, such as this cell and this cell, where in this cells where it's not the same, then it would produce the negative, which is false, leaving this output. And that's just one sample. Here's an and precip and elevation. Looking for just the ones, we would end up with just these. And can also be multiplication. Due to this, here they're and here it is multiplied. All the answers are the same. That's why we can use the multiplication. And then in this example, we do an additive Boolean overlay. We end up with 3 different values: a 0, a 1, or a 2. Because 1 and 1 equal 2, 1 and 0 equals 1, and then the 0 and 0 is still 0. We won't use the Raster Calculator per se in 3.11. And here are some more analysis techniques: reclassification, surface function, distance, density, interpolation, neighborhood functions, and zonal functions. We will definitely reclassify in Lab 8. You'll take some old values and you'll create new values. You will be going from a multitude of values on the left and breaking them down into very simple new values, just as this is showing. We'll also be using this screen where we remove these thin blue lines and add in our own lines, and certain areas of this curve will be included in our new values. In this case, we're going to be talking about surface analysis. Here we have a DEM, some slope, an aspect, hillshade, and contours. This is a slope function where it could end up being expressed in degrees or percent. Here's an aspect function, and this is the value represents a direction from 0 to 360, where 0 out of that 360 is north. Flat areas are assigned a -1 value, and in this case they are gray. In this case, we're creating an hillshade based on the azimuth and the altitude. And here's a viewshed analysis. It calculates areas that are visible from a set of observation points. So what can be viewed? This is a repeat slide, a cut and fill on a site. Some hydrologic functions to create streams, watersheds, and other hydrologic features based on the analysis of a DEM, digital elevation model. You must get very, very accurate DEM to create your watersheds or your stream layers. And even then you'll have to go in to edit some data. Distance functions, least cost path or cost path distance. And cost path could be something where the costs are increased, where there's a higher slope, which means they wouldn't go over this direction because of the steep slope. And then we go up the least steep slope, getting over to this point from this point. Here, this is a distance function. It'll be on the next page. Here's a Euclidean distance. You start from a point, line, or polygon, and it creates a grid where each cell represents distance to the closest features. And this is the furthest from the features, so this is the darker color. Euclidean direction indicates direction of travel to the closest road. Some buffer values where the road distance is less than 500 feet, where 1 would be true and 0 would be false. Which way is incorrect? You start with the same distance raster, and in this case the choice would be what you're actually looking for. You would likely, what I'm guessing is they're going to ask us to reclassify. Going from 0 to 300 would provide a 1, 300 to 9200 would be a 0. Here's some more least cost path. We don't use that in this course. What is interpolation? I'll suggest that you pause and read through this. I won't read it to you. You should also seek out some information in the book as to what exactly interpolation is. Here we have some sample point features with the climate stations with annual precipitation values, and then we have an interpolated continuous raster with precipitation values. Now it starts with these points, and then based on some other items, that branches off and creates that continuous raster. We will actually do that in one of our labs. Here we have actual elevation and then interpolation from the summits. So it is not entirely accurate or the truth, but it is a method when you don't have the actual elevation. You can definitely see where many mistakes are made between the interpolation and what the actual elevation is. Interpolation assumes that nearby points are correlated that will have similar values. 4 types of interpolation methods are available: inverse distance weighted, spline, kriging, and trend. We will use IDW in 311 and likely move to kriging for other reasons in 312 or 412. Here we have some density functions. Appear similar to interpolation, but they are calculated differently. Interpolation predicts values between points using a variety of mathematical functions. Density functions count occurrences within a given radius and divide by the area. So it's quite a different thing between density and interpolation. Simple density, it sums the attributes such as population for points within a specified radius. A larger radius gives smoother data. Kernel density first spreads out values at points out to the search radius using a quadratic formula, and then density is calculated again. This tends to give smoother results for the given radius. Using simple density, we're not going to be using this. I'm going to skip through this slide. Line density we don't use. Neighborhood statistics, we'll get to that in other courses. Window movement, we'll get to that later. Focal functions we'll move through. Neighborhood focal mean, we'll skip. Focal majority. What is a zonal function? Well, it examines and manipulates raster values in one within a set of zones specified by another layer. Zones constitute areas of a discrete raster with the same value. It requires two inputs, a layer specifying the zones, raster or feature, and a raster layer with the values to be evaluated. What is a zone? A zone is the area or areas of a raster or feature dataset that share the same integer value. Zonal statistics, watersheds and slope. Zones are defined by the zone layer, which is the watersheds, and it generates statistics for each zone from the slope, which is the value grid. The output is either raster or a table. Here we have zonal statistics of line, and we have mean slope of streams. This can be very handy when you need to know or create certain data for your analysis, which makes this is one of the more powerful features of ArcGIS. Zonal statistics of point, you can determine the elevation of the summits. We don't do that. I'm going to move on. Raster analysis example citing a landfill. I think I'm going to skip this. I'll run through it. Here's the scenario. The problem is we want to find potential locations for a new landfill using these criteria. Must be flat terrain, less than or equal to 10 degrees of slope, no more than 1 kilometer from an existing road, at least 500 meters from a stream. It must be a meadow or low-density forest. We can develop a Boolean raster for each condition, with 1 equals desirable and 0 equals not desirable. The slope condition, we use the slope function on the elevation raster and use map algebra logical operator to produce a Boolean map of slope is less than or equal to 10 degrees. The road distance condition will use the distance function to create a raster of distance from roads and use a logical operator in the map algebra to create a Boolean raster of areas within 1,000 meters of a road. And here we have close to roads, 1 being true, 0 being false. The stream distance condition, we use the distance function to create a raster of distance from streams. Using a logical operator in map algebra, create a Boolean map of areas more than 500 meters from a stream. And here we have 1 and 0. 1 is the yes, 0 is the no, or false. Vegetation. Select suitable vegetation density and create a layer from the selected polygons. Convert the selected vegetation layer to a raster using the density attribute. Reclassify the 3 density values all to 1 and the no data areas to 0. And we have a 0 and a 1. Find areas with Boolean and slope and roads and streams and vegetation, and we end up with the 1s and the 0s, and these are our potential areas. The additive model, slope plus roads plus streams plus vegetation, gives us an adding of the values, getting a 0 through 4. And now getting to specifically ArcGIS, Chapter 8, Raster Analysis. Raster formats. Input. Spatial Analyst reads any supported raster format in ArcGIS, such as grid, geodatabase, rasters, TIFFs, or ERDAS data. It stores integer or floating point values. There are other formats, but they're only for display: JPEG, GIF, Mr. SID, raw binary, etc. We can convert these, for example Mr. SID, for use as an input, however. Esri grid format. It's the oldest format. It's stored in rasters, and names are less than 13 characters and must begin with a letter. It is better to use a geodatabase and TIFF or ERDAS data. Managing rasters. Working directories tend to get clogged with grids. Copy, move, and delete rasters only with ArcCatalog. The best practice: create a geodatabase to store analysis outputs. We'll be doing that in future quarters. Zone is a collection of all cells sharing the same integer value. Zones need not be contiguous cells. They're most useful with discrete integer rasters. Grid attribute tables are only created for discrete integer grids with fewer than 500 zones. No data. Specific value to indicate any lack of data is often replaced by zeros in other formats. And in this case, there is no data, which is the white area. And in this case, in this image, the no data is replaced with the darker or black area. Converting from vector to raster. Choose one attribute field to convert on, which becomes the value in the new raster. A numeric field is converted directly to the raster. The raster type matches the input field. Short and long become integers. Float and doubles become floating points. A text field assigns an arbitrary unique integer to each input value in the attribute field. Original text values are added to the raster attribute table. We will convert from vector to raster. Converting features to raster, and in parentheses you notice text. There's some output zones, a grid value, and the text attribute that is carried over. Features to raster using a numeric. The grid attribute tables are only created for integer grids with fewer than 500 values. Converting selected features. If a feature layer has a selection, only the selected features are converted to raster. Other areas receive no data, or the no data value. Converting raster to features. If it's super complex, you should not convert it. If it's less complex, you can convert it. Convert only discrete data without too many polygons. For example, land use or land type. Raster to polygon. Each raster is assigned a grid code attribute containing the value. And here we have going from a 0 to a 1. So the grid code would be 0, 1, 1, 1, 0, 1, 1. Converting 0 versus no data. Raster contains 1 and 0 values. This raster contains 1 and no data values. The reclass function can convert 0 to no data if needed, and that would be something you'd input. A reclassify, I already talked about this. We will convert or reclassify some of our data in Lab 8. And now moving on to Spatial Analyst. Spatial Analyst is an extension to ArcGIS and is installed in the complete or custom option. Hopefully you installed it. And it requires the purchase of an additional license to use if you're buying the software. We have it. It operates within ArcMap or ArcCatalog, and it analyzes raster data. use the help function. Here we have the help function showing up. You can get to that by example here, right click, help, and then click on these items to open up new items. I would highly suggest learn more to explain some of the theories and processes behind the tools. To turn on Spatial Analyst, if you do not do this, you will get an error that will say, first of all, even though it's installed, it must be turned on. If you don't turn on Spatial Analyst using this method, customize extension Spatial Analyst, you'll get a notice that you are not authorized to use it. And this is the area that you'll have to turn to if you say you can't use it in the class when you have to go to Spatial Analyst. I will refer you referred back most likely to here, but if you're watching this ahead of time, you now know customize extension Spatial Analyst. Setting environment settings, we will do this, geoprocessing environments, and then environments. The application level are here. This is the tool level, or for example the intersect tool. This only affects the execution of this tool, whereas if we set it here, it's global. It affects all the tools and menus, and this is where I usually set mine, in the geoprocessing environments. In fact, I showed you how to do this in Lab 4, in preparation for Lab 4. Useful environment settings, output coordinates, processing extent, and raster analysis. We will set our current and scratch workspace, our output coordinate systems, the processing extent, cell size, and analysis mask. These are the most popular. Working directory, location where outputs are placed by default. Check it every session and set as needed. It's recommended to create a Scratch folder or geodatabase for rasters. We will not necessarily do that. We'll use our regular data folder. Output coordinates. We've already mentioned that grids are best stored as projected coordinate system for analyses. And unless specified, the output will match the first raster input to tool. It's not always obvious, so be sure to take these cautions and follow the directions carefully in terms of the output coordinates. Processing extent. This gives us a visual. In this case, the union of the inputs. If we have multiple rasters, that will use the union, or you could use the union. An intersection of the inputs. Right here, we'd only have this little yellow area. Same as the display, which is shown here, which is the entire area. Or same as the layer, and in this case, the layer's name is elevation, which would be this area for some reason. If you go too large, it wastes time and storage. It takes a lot longer to process when you're using much larger areas. So that's what we'll usually say the same as and choose the actual layer. And for example, same as layer elevation. Cell size option. The default is the maximum cell size of the inputs. You'd use as specified below to set a specific cell size such as 30 meters or to match it to existing data. We will set the cell size. And the analysis mask. We can set a mask. I honestly can't remember if we set a mask for our data. We will in advanced classes, but in 3.11 we may not set the analysis mask. And last but not least, something that we definitely will be doing in 3.11, which is clipping a raster or extract by mask. There is no such thing as clip raster. You have to extract by mask. It works the same way. You can use an input raster or feature to do your mask. This is most likely a feature. Here is our input raster, and this is what we end up with. this looks like a watershed. It looks like somebody took a watershed and performed an extract by mast. And that concludes Chapter 8 of Mary Beth Price's book, Mastering ArcGIS, and in this case, this was Chapter 8, Raster Analysis.